Good afternoon, good evening, everybody. Um, so we're going to focus on topic 5.9 from APES Unit 5, which is the impacts of mining. All right, our enduring understanding. So just remembering for Unit 5 that when humans use natural resources, they alter natural systems, but humans can mitigate their impact through sustainable use and using best practices. All right. To read, the reading to accompany this particular set of notes comes from sections 11.3 through 11.5, pages 311 through 322. All right. So let's quickly define what it is that we're talking about when we say the term minerals. So minerals are elements or compounds uh, that occur naturally in the Earth's crust. So some examples would be salt. Salt is a mineral. All of our metallic resources come from minerals. Quartz, which is silicon dioxide, right? Um, which is a primary component of glass. So glass is a mineral. All right. Um, Now, to contrast minerals from rocks, right? So rocks are basically naturally formed aggregates of minerals. So minerals would be considered pure substances. They're compounds. Okay, rocks are made up of a variety of minerals. So in the case of granite, for example, granite is composed of quartz, or and feldspar, and biotite, and hornblende, right? Those are different minerals that are basically kind of uh, part of a magmatic composition. And when that magma cools off and hardens, you can see those individual crystals of those various minerals, right? Basalt, also a rock, although you don't see the individual crystals in basalt because it's an extrusive rock and it cools too quickly for those crystals to form. All right, so or minerals are pure substances. Rocks are composed of two or more minerals. All right, so when we use the term minerals in this class, though, we're usually going to be referring to the minerals that have substances that we need to use as a resource. All right, so some of those abundant minerals, silicon dioxide, like I said before, which is the raw material for glass, right? Most abundant mineral in the Earth's crust. All right. Aluminum and iron, both metallic resources, but relatively abundant compared to other metallic resources. Now, not quite so abundant are things like copper and chromium and molybdenum. Those are important, and there's a fair amount out there, but they're not nearly as abundant as aluminum and iron. By the way, aluminum is the third most abundant element in the Earth's crust. All right. Um, Now, one of the things we have to understand is there's trace amounts of essentially all minerals all around us. But in order to make it worthwhile to actually try to extract a particular resource from a mineral, um, it's not so evenly distributed. There's these little pockets, right? And those pockets of a high concentration of that particular mineral are the places we go and mine for those minerals. All right. Um, and so they're unevenly distributed. Some places they're in a really high abundance. That makes that a good place to go and mine and make a profit. If it's found in low abundance, it might not be profitable unless the market price of that mineral increases over time. All right. So we're going to define this term next, mineral ores, right? So an ore is a mineral compound containing a relatively high percentage of a particular mineral resource. So aluminum ore, for example, is a mineral that has a relatively high percentage of aluminum in it. And it's those ore resources that we will usually go after for mining. All right. Um, Bauxite, for example, is the mineral in which we find our aluminum. All right. Um, Oops, excuse me. And this looks like some copper chloride and copper sulfate crystals forming there. So that's an example of a mineral from which we could extract copper. All right. So high grade versus low grade ores. So a high grade ore, as the name probably implies, is an ore that contains an especially high percentage of a mineral resource. So these are our uh, gold standard, pun intended, right? This is those high grade ores are our most profitable and also the least wasteful because in order to get a lot of a resource, we don't have to mine as much material. Now, low-grade ores can also be profitable, but just less so. And a lot of it depends on how much it costs to extract that mineral and whether it's worth that cost when you try to sell that mineral resource on the free market. If there's a really high cost for that mineral, it's going to be more profitable in those lower grade ores, right? But if it's a highly abundant mineral like aluminum, for example, those low grade ores probably won't produce enough aluminum to make it worthwhile until aluminum becomes more scarce and more expensive. All right. So how do mineral deposits form? So we talked about there's certain locations with a relatively high concentration. So there's different processes that might lead to this to occur. So magmatic concentration is an example of how we can get a high grade ore. And so as magma cools off, right? So they have different melting points for one, so it doesn't necessarily crystallize all at the same time. But magma being a liquid, it as those metals being of relatively high density, right? If they are mixed into a magma, because they're pretty high density, they will tend to settle out toward the bottom. And then as that magma solidifies, right, we might get a relatively high concentration of something like iron or copper or nickel, right, forming as a result of that magmatic concentration. Hydrothermal processes. So we talked about hydrothermal vents way back, I think that was unit one, in a different context, right? So superheated and acidic water from deep underground in the ocean um, can pull up certain metallic sulfides and concentrate those. So this is actually a little cross section of a hydrothermal vent. We can see a fairly high concentration of what looks like iron pyrite, which is high in iron. Okay. Sedimentation is another process where basically, as water runs downhill, right, heavier, denser particles settle out faster than less dense particles. And then evaporation. So for some of our non-metallic minerals like salt uh, and borax and gypsum, right? Those are relatively soluble in water, and so as the water evaporates and leaves the dissolved materials behind, we can get a high concentration of a salt or borax or gypsum. So those are some of the processes by which mineral formations with high concentrations of a particular mineral might form. All right. So here's where things get really important to us in terms of environmental science, right? So I do want to point out at this point um, that uh, we rely heavily on our mineral resources, and even with so-called green energy technologies, right? They are so-called because they tend to have a much smaller air pollution footprint or much lower impacts in terms of climate change, et cetera. But we still are going to rely heavily on metallic and non-metallic mineral resources uh, indefinitely, right? So every single modern process requires some materials that have been mined. Even your mobile phone, right? Upwards of 75 different mineral resources are required just to make that phone work. So super, super important industry and process. And it's going to be an important process moving forward, even as we transition to better technologies. All right. So to get those minerals, we have to mine them. And there's lots of different processes and types of mining. We're going to basically break it down into two main types. There's what's called surface mining, and as the name implies, that would be when our mineral resource is relatively close to the surface. It's actually the safest and easiest way to get at it. So through processes of heavy machinery and explosives, they essentially tear apart the landscape, to get to the particular resources that they're looking for. Most common and biggest mining operations are for coal specifically, but there's lots of surface metal mines as well. All right. Now, there's open pit and strip mining, which we might get to later. Then there's what we call subsurface mining. So when we have a mineral resource that is farther beneath the surface, it is more expensive to get to, which makes sense. Okay. However, it is less uh, impactful in terms of altering habitats because most of the mining and disruption occurs beneath the surface instead of at the surface. All right. So subsurface mining occurs when our mineral resource is deep underground, and it doesn't make sense to just keep scraping off the surface. So there's what are called shaft mines and slope mines, right? So these would be examples of our shaft mines. These would be examples of a slope mine. All right. So um, we've found a mineral resource that was formed either through magmatic concentration or sedimentation or evaporation or through hydrothermal processes, right? We found a way through a mining operation to extract that mineral resource. Then comes the step of processing it, right? So we extract our aluminum ore or our iron ore or our gold ore, right? We then need to extract the specific material that we want. So the bauxite, for example, the mineral that contains a high percentage of aluminum, we want to pull the aluminum out of that. All right. And the primary process by which we do that is what's called smelting. So basically, you're going to cook it out. So super high temperature process in which you basically heat the mineral ore up and that metallic material is able to essentially melt out of that ore. Um, okay, so it's done in what are called blast furnaces and smelting plants. Okay, now um, we've gone in and we've extracted that mineral through either a surface or shaft mine. We pulled that mineral to a smelting operation to purify it. Okay, so that entire process, of course, has environmental costs, right? So we're going to alter that system, but that doesn't mean that we have to do it in such a way that we leave that system in distress. So let's first talk about the potential environmental problems, then we'll talk about some of the solutions. All right. So first of all, mining, particularly our surface mining, disturbs large area and causes all kinds of habitat loss. It produces large amounts of waste, uses large amounts of water, and creates a problem that we call acid mine drainage. By the way, we're going to talk about each of these in turn. It's an energy intensive process leading to things like air pollution and sometimes acid rain. All right, so let's get into the nitty gritty of each of those. So obviously habitat destruction. So what is our number one cause of biodiversity loss? Habitat destruction. So mining operations, particularly for our fossil fuels like coal and tar sands up in Canada, uh, are particularly destructive to habitats. All right. Subsurface mining, less destructive. All right. Now, we tend to produce a fair amount of waste. So even though we call them ores and we say they have a relatively high percentage of a particular material, almost all those ores are still mostly waste material or material that we don't want. So iron ore, for example, tends to be one of our highest concentrations, but even in that case, 60% of the ore material is not usable. Sometimes, at best, 40% of that ore is actually iron. Copper, even worse, at 99% becoming waste. Gold, 99.99%. Right? Now, notice though that the value of those metals tends to increase, right? As the amount of waste also increases. Part of that has to do with the cost of extracting that material. Notice aluminum and iron are relatively low cost metals compared to things like gold. And copper is more expensive than things like aluminum and iron as well. All right. So the waste material. So after we've extracted the material that we want, we are left over with waste material that is referred to as tailings. And those tailings often have higher concentrations than normal bedrock of toxic materials like lead or arsenic or cadmium, things like that. Okay, the smelting plants that extract the particular, so the one material that we do want out of that ore, uh, they emit large amounts of air pollutants, particularly sulfur oxides, right? Which can then lead to acid rain or acid precipitation. So acid rain, we'll discuss more in our Unit 7, which is a unit specifically on air pollution. But for this point, what we have to understand about acid rain is it's not like it falls on you and like if you were outside and acid rain hit your skin, it's not as though it would cause like severe irritation to your skin. What it is it's rainfall with a lower pH than normal rainfall. And because of that lower pH, it is sometimes better at dissolving minerals away. All right. So it's going to cause increased leaching in our soil, uh, leaving our soils barren of nutrients, killing off forests and things like that. But again, that is a topic that we'll talk about more in a later time. Okay, and it requires lots of energy. So Unit 6, our unit on energy, will talk about big concerns around energy, but uh, things that are energy intensive processes tend to have very large carbon footprints, which leads to has all kinds of implications for climate change and so on. All right. Now, a topic that we're only really going to talk about here in this unit is this topic of acid mine drainage. So again, we have large amounts of sulfur containing compounds. So sulfur, by the way, is one of what they call a universal contaminant. It's found just about everywhere. All right. And so as water percolates through bedrock materials naturally, it does going to pick up a little bit of sulfur, which might cause the pH to drop a little bit naturally, and that's okay. Now, in and around our mining operations, though, what we've done is we've disturbed the sediments and bedrock enough that we're exposing water that does fall to a much higher amount of sulfur than normal. All right. Um, and so as that water picks up those sulfur compounds, uh, we tend to form what's called a sulfuric acid compound, or sometimes a nitric acid, um, or a carbonic acid, depending on what type of sediments it goes through. All right. But usually with our acid mine drainage, we're looking at the water picking up sulfur compounds, which might go through some reactions with the water to form a weak sulfuric acid. Now, that acidic water flows out of our mining area. All right. Now, what is particularly problematic about that acidic water, right? Again, is not so much that it's going to immediately cause like tissue damage, although potentially it could, right? It's that acidic water is better able to dissolve certain materials. Now, in this case, we're mostly concerned with our acid mine drainage about toxic metals, right, becoming more soluble in the water. So things like lead, cadmium, and arsenic, which are quite dangerous to living systems, right? So normal rainwater would not dissolve very much lead or cadmium or arsenic, right? This more acidic water that flows out of our mine is able to better dissolve those and then carry those into our waterways. So really, the big concerns from acid mine drainage are poisoning that water from these toxic metals. All right. So a really good case in point that's from my old textbook, in fact, but it's the Copper Basin in Tennessee. Um, so this is supposed to be a forest, right? Looks like a desert, but it is supposed to be a forest now, and this is a direct result of leaching and soil erosion caused initially by heavy smelting, which led to acid precipitation. Right? So the acid precipitation falls, leaches the nutrients out of the soil, kills the forest. The forest is no longer there to provide the ecosystem service of maintaining the soil quality. Intensive soil erosion, intensive nutrient mineral depletion, right, led to this desertification of the Copper Basin in Tennessee. All right. So, um, mitigating issues caused by mining. So we have what's called the Surface Mining Control Reclamation Act of 1977. Two other important things happened in 1977. One, the first Star Wars movie was released. Two, your environmental science teacher was born. But more importantly, in this context, is the Surface Mining Control Reclamation Act, which mostly just applies to our coal mines. Okay, but it did set standards. So when these mines finish up, they extracted the material that they need to extract. They don't get to just abandon ship and let it continue producing uh, acid mine drainage and stuff. They have to go back and reclaim that land, right? And set it back to some sort of productive purpose, ideally a natural system, right? So the goal of restoring our mining land. So after we've extracted that valuable resource that we do rely on, right? We need to go back, prevent further degradation, um, eliminate local sources of toxins, and make the land productive again. All right. So how do we do that? First of all, if there was a surface mine, we're gonna replace that overburden. Overburden, by the way, is the stuff that we move out of the way to get at the resource. Let's say we scoop away some layers of rocks and other sediments, get to our coal seam, right? We pull the coal out, we put that overburden back. That's replacing overburden, right? So overburden is not the same thing as tailings. Overburden is just the material we move out of the way, right? It's not toxic, etc. Tailings are waste left over after smelting, which often are toxic and have to be disposed of differently. All right. And overburden, of course, again, mainly a problem in our surface mines, as beneath the surface, we're not moving large amounts of material out of the way. We're kind of going directly to those mineral resources. All right. So after we replace the overburden, we then need to do something about this acid mine drainage. And there's a couple options. One is what's called carbonate neutralization using calcium carbonate, so limestone. And we did talk about that back in our carbon cycle unit. All right. Now, carbonate materials, calcium carbonate, are relatively good at neutralizing acids, right? And so, if we have an outpouring of water from a mining area that we know is going to have a lower pH because of excessive sulfur compounds being dissolved in that water, we could then put some carbonate rocks in and around the area where water is draining out of our mines, and that will help to neutralize that acid and get those nasty metals like lead and arsenic to settle back out of solution before it gets to our local waterways. So that's what's called carbonate neutralization, and it has relatively limited effectiveness because sometimes our outpouring of or runoff is dispersed in nature as opposed to being in one localized area. All right. Now, another more effective way that works more slowly and is a little bit more intensive of a process up front is to construct wetlands. All right. So wetlands, as you guys learned back in our biomes unit, are nature's filters, right? They have all kinds of bacteria and fungus and protozoan and archaea, right? That are really good at breaking some nasty compounds down and filtering and cleaning that water as it goes out. Not only that, they help prevent flood control and help prevent erosion. They're slow acting, but very, very effective. All right. Um, then we got to manage sediment and erosion in the short term until vegetation has a chance to come back in, go through that pattern of succession, and reestablish itself and hold that soil in place. Right. So you can create sediment ponds, right? So a place for water to collect where sediment can settle out so it doesn't get into our local waterways, right? But again, the big thing we need to do is plant vegetation, right? Get some trees if the climate supports that, or grasses, etc., back there to help hold that topsoil in place to help prevent that sediment and erosion. All right. Um, Now, some other creative approaches, right? So let's say we have contaminated soil, right? It's a mine, right? We've got some waste material left over, and we have high amounts of some really nasty things like cadmium or arsenic, right? We can use a process called phytoremediation, right? It's a really creative approach. Uh, so sometimes certain plant species are relatively good at taking in toxic metals and incorporating them into their tissues, right? In fact, they're actually using this out at Hanford to help clean up some of the radioactive waste out there, that's radioactive material that's in the soil, right? So essentially, they'll uptake that and bring some of those toxic metals like mercury and stuff into the tissue of the plant and disperse them into the atmosphere, or incorporate them into their tissues, after which we can remove those plants and dispose of the plants and be left with healthier, cleaner soil, less toxic. All right. Then ideally, right, we want to leave the mine back in such a state that wildlife can come back in and reclaim, and we have a fully functional ecosystem again. So again, taking this back to the main points and enduring understandings of Unit 5. Humans do alter natural systems when we extract resources, but we can mitigate many of those disturbances uh, if we incorporate best practices and try to return those systems back to their original state. It's not always easy, as we talked about with forest management, but there are things we can do to have a much smaller degree of impact in the long term if we incorporate those best practices.